Hello, math humans. We're going to do 2.1a today. We're going to be talking about the limit definition of a derivative. So our objectives are that we're going to find a derivative using the limit definition of a derivative. So let's go back and talk about the tangent line problem. We introduced that on our very first day. So let's say I have a curve that looks kind of like this. So this is my function. And then I want to find the slope of the curve at this particular point, C. So if you'll remember, we talked about the tangent to the curve at point P. Okay, the slope of the tangent can approximate the slope of the function at point P. Alrighty? And so we talked about, if you'll remember, talking about a secant line that can run through. So we found the slope of a secant line. And then what we did is we talked about making, so if this is x1 and this is x2, and the difference is delta x, then we said the slope is the change in y over the change in x, and so that would have been f of x sub 2 minus f of x sub 1 over x2 minus x1, right? And so what we want to do is talk about what happens. So I can use the secant line. I want to take the limit as delta x goes to 0, okay? And as delta x becomes smaller and smaller and smaller, so if I draw some different ones, is maybe my next approximation is here, and then maybe the next approximation is here. As delta x goes to 0, then the slope of the secant is going to be more equivalent to the slope of the tangent, which is more equivalent to the slope of the function. So it's actually really a cool process by just taking the limit as delta x goes to 0. So then we would write the limit of f of c plus delta x minus the original function, oops, that should be a c, over delta x. As delta x goes to 0, then this is going to be the slope of the tangent line. And all I'm doing is I replaced c with x. So if I take the slope of the function and then the slope of the function plus delta x, subtract the original function right here, and then divide by delta x, then I'm going to get the slope of the tangent line, which again is the slope of the function at a specific point, because remember that the slope changes at every point along the curve. So now what I want to show you is some notation. So I want to show you that f prime of x, so we say that as f prime of x is equal to the derivative, which is equal to the slope of the function at a specific point. I can do the limit definition, so I can say the limit of f of x plus delta x minus the original function all over delta x as delta x goes to 0. This is the limit definition of a derivative. And I can also write, so I can say f prime of x is a derivative, which is the derivative of y with respect to x, which is the limit of f of x plus delta x minus f of x all over delta x as delta x goes to 0. All three of these things say exactly the same thing. We just use different notation. It is very important that you become comfortable with the notation, and then we start using this appropriately. So let's start off with an example. So for example 1, it's going to say find the slopes of the tangent lines to the graph of f of x is equal to x squared plus 1 at the points 0, 1, and negative 1, 2. Okay? Alrighty. So I want to look at this that's an A, before we actually start. X squared plus 1, if this is a 1, looks like this. So I want to find the slope of the tangent at this point, and I can already tell you that the slope is going to equal 0, but we'll find it mathematically. And then at a negative 1, 2, I want to find the slope of that tangent line as well. All right? We can tell that the slope on this one is going to be negative, and so that's just kind of a way of checking. All right, so if I start to do my math, I'm going to say f prime of x, and I'm just going to write this out so we get used to the notation, is equal to dy dx, the derivative of the function with respect to x, and then this is going to equal the slope of the tangent line at a point, and we're going to do it with the limit definition of a derivative, which says that the limit of f of x plus delta x minus f of x as delta x goes to 0. So I'm going to start this process with my function. So I'm going to do this math. So this is going to be the limit. The unfortunate thing about solving a problem with a limit is that I have a lot of notation to write up. So the first thing that I'm going to do is I'm going to evaluate the function at x plus delta x. So it's going to be x plus delta x quantity squared plus 1 minus the original function x squared plus 1 over delta x. Okay, and it is very important that you show all of this math. You may not skip steps. You also have to carry this notation throughout the problem until you do your direct substitution. So this is the limit as delta x goes to 0 of x squared plus 2x delta x plus delta x squared. All I did was expand the binomial, so a plus b quantity squared, square the first term, double the product, square the last term. And then here's the plus 1. Then I have minus x squared minus 1 over delta x. Now it looks messy, but if you'll notice, a bunch of things cancel. The x squareds cancel, the 1's cancel. Now you'll notice that I'm just going to write this out just to make it neater until we get used to this process. So I have 2x delta x plus delta x squared over delta x. If I tried to take the limit by doing direct substitution, this would be the indeterminate form because the world would explode. So that means that I have to do some algebra to eliminate the delta x. So what I'm going to do is delta x goes to 0, so I'm going to factor a delta x out of the numerator, and I get 2x plus delta x over delta x. You can't skip steps. You have to show that you've done the factoring. These two terms cancel. Now I can do my direct substitution. This guy goes to 0, and I'm left with 2x. So let me tell you what this 2x represents. I have found a generic, actually it's not very generic, I have found an equation to calculate the slope of the curve at any is the keyword, point. So by using that, the derivative f prime of x is equal to 2x. That means that this is the rule to calculate slope. Okay, so we found the derivative. This is nice. So now we want to go back and read what the problem actually asked us to do. They said find the slopes of the tangent lines. This is the rule that allows me to calculate the slope of the tangent line, but I need to evaluate it now at these 2 points. So I'm going to do f prime of 0, and I'm going to get 2 times 0 equals 0. So that says that the slope at the point 0, 1 of the tangent line is going to equal 0. And if you'll remember, I told you that was going to be the case when we first drew our picture. The slope of the horizontal tangent is 0. So now I'm going to do the derivative evaluated at a -1, so I get 2 times a -1, which is a -2. Remember also that, you can't see that I told you that the slope of this point over here was going to be negative, and indeed we found that the slope of the curve at that point is negative. So the slope evaluated at -1, 2 of the tangent line is equal to a -2. Let me show you a different type of notation. So I would say the slope of the tangent evaluated at 0, 1 is equal to 0. This straight line with the point at the bottom shows that I am evaluating this situation at that point. So then the slope of the tangent line evaluated at -1, 2 is a -2. I will use this notation a lot as we move through the rest of the semester. So this is kind of a handy thing to get comfortable with. All right, let's do our next example. So this is going to be example 2. And I want to find the derivative of f of x is equal to x cubed plus 2x using the limit definition of a derivative. Alrighty, so keep your shorts on because we have a lot of algebra to do. So before we get started, I'm actually going to show you, because I have something cubed, remember that a plus b cubed, if we use the Pascal's triangle, the coefficients are 1, 3, 3, 1. So this is going to be 1a cubed plus 3a squared b to the 1 plus 3a to the 1 b to the 2 plus 1b to the 3. So in case you remember, the first thing is going down in power. This one is technically a to the 0. The second thing is going up. This is technically b to the 0. And so this would be a plus b cubed expanded. So my limit definition of a derivative is going to be the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. And this is important. This is called the limit definition of a derivative, and this would be one of those things that I add to your formula sheet because you need to be able to regurgitate this in its entirety. So now as I start my process, okay, it's going to be the limit as delta x goes to 0 of x plus delta x quantity cubed plus 2 times x plus delta x minus x cubed plus 2x all over delta x. And it's really important that you make sure that you use your parentheses. So now this is the limit as delta x goes to 0 of x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x minus x cubed minus 2x all over delta x. And as you can see what's happening, when I eventually get around to doing the direct substitution, I'm going to have the indeterminate form, so I'm going to have to do some algebra. So the next thing that I need to do is eliminate, things will start to clean up. I have a positive 2x and a negative 2x, and then I think that's all that I can cancel. So now what I need to do is I need to factor as delta x goes to 0. I'm going to factor out a delta x, and I get 3x squared plus 3x delta x plus delta x squared plus 2, and then it's going to be divided by delta x. Notice that the delta x is now canceled, and so now I can do my direct substitution. As delta x goes to 0, this term goes to 0, and this term goes to 0. And so the limit is going to be 3x squared plus 2. And so then I would write my, remember I have to answer the question that's asked. F prime of x is equal to 3x squared plus 2. I could also report this as dy dx is equal to 3x squared plus 2. And I could write out the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0 is equal to 3x squared plus 2. And remember, just so you think about what we just found, we found a rule to calculate the slope of the function at any given point, at any point. This is the rule, this is the derivative that will allow us to take the slope of the curve at any point along the curve. Alrighty, that is it for today. I will see you soon.